thought I was recording, but anyhow, here's definition. Well, here's electric potential difference. We developed the idea last time. And we developed it talking about what happens if you connect these leads to this battery. Okay, you get an electric field from one end and the other. Okay. One example of potential difference not involved with the unit charge. This is not relevant to that situation. But the example that we used is potential difference 155 volts. Long uniform conductor. "30 centimeters long" is E equals potential difference, and your book uses capital Phi. So I'll go ahead and use that. I just noticed the book uses capital Phi. I mentioned last time we often use Phi for potential difference. I think we did in multivariable calculus too. Anyhow, it's Phi over, let's say delta X. Phi is your potential difference, and delta X is your distance. Okay, which is 1.5 volts over 0.3 meters, which is 5 volts per meter, which is the same as 5 newtons per coulomb, and newtons per coulomb is your unit of electric field. And you want to think about these units, what they're telling you. Okay. A volt is a joule per coulomb. If you divide a joule per coulomb by a meter, you divide the Newton meter per coulomb by a meter, leaving you a Newton per coulomb. And we did this in some detail last time, so if you need to check on the video, that's okay. It's an intuitive concept. What happens in that conductor then is that every electron, every free electron, is accelerated by a force due to this electric field, 5 newtons per coulomb. Okay, well, what would the acceleration of an electron be? Now I'm just going to ask for the approximate acceleration. Electron mass is 9.11 times 10 to the negative 31st kilogram, which is approximately then 10 to the negative 30th kilogram. Because 9 is close to 10. 10 times 10 to the negative 31st is 10 to the negative 30th. So just using this approximation, how are you going to get the acceleration of the electron? Okay, so acceleration, everybody have the intuition that you would divide a force by mass. Now, the first answer I got was divide the electric field by the mass, but the electric field is not a force. It's a force per coulomb, which is a force per unit of charge. Why does the electron get accelerated? Because it has a charge. What's the charge in the electron? Well, something you just got to know. 1.6 times 10 to the negative 19th coulombs multiplied by the 5 newtons per coulomb gives you the force. And you divide that by the 10 to the negative 30th kilograms. And what do you get? You get 8 times 10 to the 11th meters per second squared. So in a second, the thing would be up to 8 times 10 to the 11th meters per second, right? Is that a lot? Well, 10 to the 11th is 100 billion, right? So it'd be close to a trillion meters per second. And of course, that's impossible. Well, this is impossible. This is almost 300 times the speed of light, okay? So it's not just impossible, it's way impossible, okay? Meaning, if you accelerate at this rate for a millisecond, you'd still be up to 8 times 10 to the 11th meters per second, wouldn't you? And speed of light's 3 times 10 to the 8th meters per second, so you can't accelerate at that rate for a millisecond. Okay, for a microsecond, yeah, you could. Okay, in a microsecond, you'd be up to 8 times 10 to the 5th, okay, 800,000 meters per second. Make sense? Now that's not even very relativistic. Okay, relativistic means as you approach the speed of light, it gets harder and harder to accelerate. It has a greater effective mass. It's such that it would take infinite mass to get into the speed of light. There's a simple thing that we could derive at the level of this course to tell you why. We haven't had time to do it. We're not going to have time to do it. Look it up. I think it's probably in your book. Okay. So we have this. So in a microsecond, you get up to, let's say, a ballpark million meters per second, right? If you got up to a million meters per second in a second, how far would you travel? I'm sorry, a million meters per second in a microsecond. How far would you travel? Okay, so accelerating at this rate for a microsecond, let's say from rest, an electron would get up to 800,000, almost a million meters per second, right? In a microsecond, moving at a million meters per second, it would move a meter, but accelerating uniformly from rest to a million meters per second, its average velocity would only be half of a million meters per second. Half a million meters per second for a millionth of a second is half a meter, only this far. And it's actually only 8 times 10 to the 11, not quite 800,000, not quite a million, so it's only about 40 centimeters. Well, in a conductor, electron is not going to move 40 centimeters. Okay? Electrons going to run into something. There's all kinds of stuff. There's a whole cloud of electrons. They're bouncing off each other all the time. It doesn't even get a nanometer, most likely, depending on the density of the electrons. Okay, just want you to have that perspective, because that's why these electrons are bouncing around. They're getting accelerated like crazy, but almost instantly they bounce off of something, which means that the whole cloud drifts, as we talked about in lab last time. And we want to bring this into that general picture of what goes on in a conductor. Now, the chapter we're in is not about conductors, but this is wholly relevant, and maybe the easiest thing you can see, the easiest example you can see of an electric field and the relationship to potential. So you want to understand this example for many reasons, because we will go into that for too long. Okay, well, let's change gears and go to a different situation now. Let's say you got a charge here of 5 microcoulombs. And you have a point here, anywhere, get a distance of let's say 30 centimeters. Okay. And you want to move this charge here. Let's go ahead and give this charge. Let's say this is a 3 nanocoulomb charge. We want to move it to another point here. That's only, let's see, that's 12 centimeters. Okay. How much work? To follow this path to here. Now, assuming that's something I can parameterize this path. Having parameterized this path, I can break it into little segments. And in each segment, I can figure out the electric field, right? Then I can figure out the force due to the electric field. Take the dot product of that with the displacement and just do a simple line integral. I've got a parameterization of this path. As you know from autographical calculus, I hope that's easy. If the path is parameterized, you just partition things. However, that's a little beyond the level of this course. So you'd be glad to know if I could ask you to do that in this course. Next course, we have electromagnetism. You're going to be prepared to do it, though. Okay? If you go further with electromagnetism, that becomes what field you're in. Okay. So we're not going to do a line integral to figure this out. Why? Because this is a conservative field. The result depends only on initial and the final point. Okay? So calculate this line integral if you wish. All you have to do is use the potential. So what's the potential? At 30 centimeters, what's the potential at 12 centimeters? The answer goes back to that Q thing. All right, so I changed from 5 microcoulombs to 6 because you went from 6 easier to do with that. Okay. Easy to divide 30 into 6, easy to divide 12 into 6. Your potential is KQ over R. There's what it is. So phi 1 and phi 2 would be KQ over R1, KQ over R2. So the change in phi is going to be KQ over R2 minus KQ over R1. You factor out the KQ and you get this. That should be obvious. If it isn't, make sure you take a good look at it later, okay? Now that you have this, you want to get a numerical result, it's a good time to do it, okay? If you do this and this separately, you got to figure out KQ twice. If you do this, you have an elegant expression that takes less work because you just got to figure out KQ once. And actually what we're looking at then is potential difference. I do this symbolically, I do this symbolically, and then I get my potential difference. Use capital phi, I'll use capital phi. And they also put a sub E on it because it's electric field. When we start talking about magnetic potentials and stuff, or other kinds, then we'll put the E on it to distinguish an electric from a magnetic, okay? So let's see what you're asking here. Okay, now implicitly, we're looking at the motion of this charge through the field of this charge. And we don't want a moving field, we want a fixed field to calculate this. And I didn't write out the entire statement, but it's clear that this moves from here to here. And we want to find the potential due to the field of the 6 microcoulomb charge. Again, if we wanted the potential due to this thing, since it's moving, we'd be fine. Okay, that's just much more complicated. So we have a fixed field, KQ over R, where Q is your 6 microcoulombs. So now we just have to put the numbers. Well, that's easy. KQ, 9 times 10 to the 9, multiplied by 6 times 10 to the negative 6, right? Gives you 54 times 10 to the third, negative third. Now 54 times 10 to the third. Wait a minute. Yeah. Which is 5.4 times 10 to the fourth. It's Newton meter squared per Coulomb squared. Multiplied by Coulomb, so it's Newton meter squared per Coulomb. And you got 1 over 0.2 meters minus 1 over 0.3 meters. 0.12 meters, 0.3 meters. Now you can deal with that fraction. It'd be like R1, R2, sorry, R1 minus R2 over R1 times R2. And you get the number relatively easily. I'll let you work it out. But what are the units of this calculation going to be? You've got Newton meter squared per Coulomb here, right? And you've got meters in the denominator over here. Well, that's going to give you Newton meter squared per Coulomb divided by meters, right? The difference in these reciprocals is the reciprocal meter. That's Newton meters per Coulomb, so that's going to be joules per Coulomb, isn't it? So now you're just going to get a number. What's your number? Okay, well, it comes out pretty easily. You can actually kind of calculate this in your head. 1 over R2 minus 1 over R1 is R1 minus R2 divided by R1 times R2. Well, R1 minus R2 is 0.18 meters. Yep. And 0.12 times 0.3 is 0.036. Okay. And 0.036. 36 goes into 18 half. 36 is 18 is half of 36, but you got the 0.0 and the point, and it leaves you 5. Okay. So you have 5 times, this is 5. And then you have 5 times this, which is this. Okay. 5 times 5.4 is 27. Make that a 2.7. Goose up the exponent a little bit. Okay. I just mentioned that because if you do the algebra enough and look at it enough, look at the numbers, you've got a little bit of ability to do mental calculations. That's not a hard one to do. And just let's look at the algebra of volume and fraction, which we're looking at. Okay, well, anyhow, that's Now, normally we write this in scientific notation, 2.7 times 10 to the fifth, but the idea is Newton meters per coulomb, as we saw before, is joules per coulomb, which is volts, right? So you got 270,000 volts. Okay, well, that's actually quite a bit of charge put at a point. That it can more or less be done, at least on a small sphere. But, you know, you Van de Graaff generator, whatever, you know, it'll shock you. Get close enough to it, that field jump at you, and get a static electricity shock, which wouldn't hurt you, but unless you have to jump back and hit your head. So, okay. Okay, well, just a little perspective. Okay, so we have this. How are you going to get the work? Obviously, the more charge you have here, the more work it's going to take to overcome this field, right? So how does a 3 nanocoulomb charge come into this? Okay, let me go ahead. Okay, I wrote this down with recording on. But, you know, the work is just your Q times your delta V. Your charge times your change in potential, because charge is in coulombs. Potential is in joules per coulomb. You're going to get joules, okay, just by the units. And that's a good way to relate to these very simple relationships and build up more intuition about what they really mean, okay? Then you get used to the relationships, and you can use them symbolically with some confidence. So this is a little hard to read, but you multiply your moving charge here. Charge is moving through the field times the potential difference between these points in that field. Okay. And the calculation is very simple. You end up with 8.1 times 10 to the negative 4th joules. That 10's kind of poorly written there, as is everything else before. Okay. So you really want to understand that example. You want to review these things because they give you insight into the homework that's due and all that kind of stuff. Okay, they give you an example. You want to read the examples in your book. You want to do the problem and do them in such a way that you're learning the material, because you can always get by them without learning much. Okay. Okay, well, one example. Now, next question, what if we have a whole bunch of charges? I'm going to do this symbolically because it's a simple idea. And if you do it for one charge, you can do it for another. So if we have Q1 at the point X1 Y1, Q2, X2, Y2. And we want to find the electric potential at the point. We'll call this S naught Y naught. So in symbols, what do you think the potential would be? Okay, now what I see is people tending to write down a pretty simple expression that has the right idea, Pythagorean theorem, okay? But I wasn't seeing quite the right expression. So I asked the question, well, what if you're more than 78 miles away? Okay, now needed correction, that was pretty good. Okay, well, your picture. And you kind of mess up the picture here, but so here would be your R2, the hypotenuse of the right triangle, right? And the right triangle doesn't have sides, doesn't have length, sides x2 and y2, has sides x2 minus x naught, x2 minus x naught, and y2 minus y naught, right? So this would be like this, and of course, R1 would be x1 minus x naught squared, and you can have that for 2. Okay, I'm not going to fill in the details, but then you're just going to have potential is KQ over R1 plus KQ over R2. Which we could write, of course, as KQ times 1 over R1 plus 1 over R2, which we could even write as KQ times R1 plus R2 over R1 times R2. And R1 and R2 are the expressions in terms of X2, X1, Y1, X2, Y2, and X naught, Y naught. R2 would be this. R1 would be the corresponding expression at subsequent point. Okay. Well, that's an important picture. If these two charges have opposite, or these two charges have opposite signs, then there are points where the potential is 0, right? Okay, matter of fact, there are paths along which the potential is 0. So it could be, well, if these charges are equal and opposite, with the picture, because now we know how to do calculation. So we got Q and negative Q. So that our KQ times 1 over R1 plus 1 over R2 equals 0 when 1 over R1 plus 1 over R2 is 0. Okay. Well, okay. I didn't say that very well. I mean, your KQ over R1, you're going to have KQ over R1 and K times negative Q over R2, right? Or you know, vice versa, whatever. That occurs if R1 equals R2, if these charges are equal and opposite. So everywhere on this line, which is supposed to be the perpendicular bisector, those distances are equal, right? Right there's a perpendicular bisector, the line between the points, and that's going to be what you call the zero potential line. So you move for free anywhere along that line. It'll work. And there are other lines. 1 over R1 minus 1 over R2 equal any constant gives you a line, or gives you a curve. Okay. So like if you're here, maybe twice as close to this one as you are to this one. At every point where you're twice as close to this one as you are to this is another, call it an equal potential line. The potential would not be zero, but it would always be the same. Those set of points that are twice as close to this one as this one, and well, it's a conic section. Which is why you need to know conic sections. Okay, if you missed that in calculus, you probably missed it completely, so you really need to kind of get into it a little bit. So I'll let you puzzle over what that might be, but that's the idea. You get equal potential lines. People use examples of equal potentials for other configurations. For a single point charge, any circle concentric with the charge is an equal potential line. Because on any circle concentric with the charge, if you move on any circle concentric with the charge, you're never changing your distance from the charge, so KQ over R never changes. Well, it's totally analogous to what happens to a circular orbit around a planet. A circular orbit is an equal potential line. That's why you can stay in orbit for a long time if you hop far enough that the atmosphere doesn't interfere. Of course, the atmosphere does interfere, which is why you got to boost satellites eventually. The further they are from the Earth, the less atmosphere. Pretty soon, you don't really have to boost. Nobody's boosted the moon's orbit for a long time. I remember we used to try to do that. It's kind of cute. Okay, we're a little worried about it before we really understood. So I'm that old. Okay, so anyhow, there we have it. So those are equal potential lines. Okay, if you have a line charge, well, if you look at it and all under equal potential lines or circles or cylinders around this charge. Okay, it's hard to draw that. But as far as anybody looking at the tell, I'm holding up an infinite rod. Okay, now common sense says it probably isn't really infinite. Another point about this rod is that at points that are much closer to the rod to the end than to the ends, The rod is pretty essentially infinite. You can work out the calculus of that pretty easily. Okay. Now, any cylinder concentric with this rod, your field that is inversely proportional to how far you are from the rod. Okay. That means your potential, and I think you're going to see this, or you've already seen it, maybe I'll derive that one, is a natural log of R. Okay. Relative potential relative to the center of the rod, to the axis of the rod. All right. Well, we can work that out. But the natural log of R is constant as long as R is constant. So for any circle, any cylinder around this conductor, you can move from one point to another with no work. That cylinder is an equipotential surface. Okay, so that came up. Let's work that one out. Now, where did this come from? We integrated the electric field from one point to another. Okay. So let's, I'm not worried about the 2 pi k's and lambdas and all that stuff. Let's just say that E is some constant over R. If we derive that from Gauss's law, you can easily derive it, and you should be able to do that, since we spent a whole class on deriving Gauss's law, or using Gauss's law for the charge of a point charge or a line charge. And you need to understand it also for plane charge. That was in, I think, the last chapter. Okay. Understand why this is so. If you don't understand immediately why this is so, you need to review that. Okay, so constant over R. What are the units of the constant? Well, the units of the electric field are newtons per coulomb. That's got to be equal to the units of the constant over the mass, over the over meters. I read that as mass, so somebody else could. Okay, so constant is in Newton meters per coulomb, which is joules per coulomb. Okay, so M view an infinite line charge is here. Got one point of distance R1, another point of distance R2. You got a test charge. distance R1 to distance R2. The field is conservative, so you move along any path. Okay. So here's our charge. Well, here's our line charge. That's the end view. We have the line charge. I'm going to choose to move along a straight line from distance R2 to distance R1. Distance R1 to distance R2. There's a point in between here. Think of an increment along this line. You have a sample point. Typical increment of length delta Ri with sample point Ri star. Then the work contribution on interval on the ith interval. Okay, this your ith interval, ith increment. We'll call delta W sub I. What's that? It's force times delta R sub I. What's the force? Well, that's on a test chart. I knew I had that written somewhere. QT. Force in QT is you move from here to here. It's a force? No. Like force is the electric field times your charge, right? So it's electric field. All right, this was charge times the electric field, EI star, delta Ri, where a star and an I always refers to something calculated at your sample point. For small increments, that's going to be very close to the average value of whatever the constant, whatever the quantity is. That's then QT times whatever your constant is. Over Ri star, delta Ri. So the total work is the sum of the W sub i's, which approaches the integral of QT times your constant, which I don't have room to write out at the start of it. From distance R1, distance R2. I've got that tracked in there pretty well. But we partitioned from R1 to R2, right? So when we do the sum of the work contributions of the increments, which are again force times distance on the increment, force being test charge times the electric field, and the electric field being some constant over the distance r sub I for given increment. We sum all that up in the usual manner and we get this interval. So now your work per unit charge is the integral from R1 to R2 of QT times your constant over R dr, all divided by QT. So just real quickly do that integral. Again?
Log R.
Yeah, natural log.
Yeah.
Right. Better say natural log, but that's what you meant. So it's a natural log, right? Now there's antiderivative of 1 over R, the natural log of R. And you got to evaluate that between the endpoints, right? Okay, so we saw that. That's good. I was thought you would. I was certainly hoping you would. Because I knew you learned something in calculus. I was recording. Okay, I don't know what I've been recording, what I have. I'm pretty sure I've got it all. Okay, again, here we've derived the field of line charge. Okay, but, not the field of line charge, the potential of the line charge. This is an integral, work integral, divided by your arbitrary test charge. Okay. And the work, of course, depends on the test charge. Test charge is down here. That's constant. This is constant. So all that comes out of the integral. QT divides QT, goes away, doesn't matter. And you end up with your constant times the integral from R1 to R2, 1 over R dr. So I just repeated that here. And I think I recorded that when I did. You know, that's your potential. Integral 1 over R, Brett told me it's natural log of R, that's good. Natural log of the absolute value of R, so you got to be careful about that, except you don't because R1 and R2 are both positive, so the absolute value in this case makes no difference. You get constant times natural log of R2 minus natural log of R1, which I should have put into parentheses, right? So how do we express that in terms of properties of logarithms? Okay, well, simplifying this goes all the way back to pre-calculus, but if you did integrals of this nature,
Take it to the E.
a log of A over B is a log of A minus a log of B. Something nobody in my generation will ever forget because we actually had to use all those properties to do calculations. Just routine calculations. We learned that, you know, before we took chemistry and used it all the time, all the way through. You don't have to do that now. So you don't understand the properties of logarithms, like those of us who grew up back in the Stone Age. Okay. But you got to keep track of them. They're easy, but you have to understand why they work. Okay, so you really want to kind of keep that in your toolkit. Okay. in general, your electric field's a gradient of phi. Now your book has some equations in here. Okay, actually your book uses V instead of phi in this case. So just to keep it consistent, I think your book does. I'm looking at a printed copy. You've got an online copy, and anything can happen, but I'm pretty sure they're going to keep this notation consistent. Okay. And what's the gradient of V? It's Vx times phi plus Vy times K plus Vz times K. So if you remember anything about the gradient from lower level calculus, then you really should, and using this to remind you of things you should know. You're not required to know that this is the gradient, but that's the easy way to see what the book says, which is that Ex equals Vx, Ey equals Vy, and Ez equals Vc, where this is a derivative. You know, I'm using a notation here, but now I'm going to write it out more explicitly. I'm using the subscript X, Y, and Z for derivatives, but we're also going to use it for components. So I'm not going to use that notation for derivatives. And let me make sure that I'm representing. Yep. Okay, that's what they use. I use E1, E2, and E3, so we don't have confusion with partial derivatives. But the text is not written for somebody who knows what partial derivatives are, although text is great for review, even if you know all your molecular constants and differential equations. So I'd use a different notation, but I'm not equivalent with these guys because it's a great textbook. I learned from an early edition on stone tablets. And have used it throughout because even though I've experimented with other books, students seem to like it the best. And naturally, I'm really comfortable with it. Okay, so anyhow, this tells you that Ex is this, and Ey is this, and Ez is this, and you don't need a bunch of formulas to understand that. So it's just a little more compact in your mind. It's a little more powerful tool in your toolkit to understand this in terms of the gradient. And you also, your gradient and conservative fields and the relationship between potentials and gradients and stuff like that is important in most areas of engineering, okay? So you want to reinforce it.